Well, it's a great honor and privilege to be involved with the Abel Prize. It is also an honor and a privilege to talk about the work of a mathematician as wonderful as John Milnor. I have to confess to feeling rather nervous about this because it is not my area, but I'm hoping that will actually work slightly to my advantage in a sense, because there are plenty of people here who aren't even mathematicians, and maybe it would be better to have the work presented by someone who shares a sense of just how strange and difficult this mathematics is. But let me begin by something that's not so strange and difficult, a little puzzle that you might see on an IQ test. Let's take a sequence that starts 1, 2, 5, 14, 41, 122. The question is, what's the next number in the sequence? I don't want to dwell on this too long, but if you're feeling sharp, you may have noticed that each term in the sequence is 3 times the previous term minus 1. So the next term is 322, that makes 366, minus 1 makes 365. So if you're feeling that that was a bit too easy, here's another question. A different sequence of numbers. 1, 1, 28, 2, 8, 6, 992, 1, 3, 2, 1, 6, 2, 5, 6, 2, 16, 16, 5, 2, 3, 2, 6, 4. What comes next? Well, I'm not going to tell you just yet, but I will reveal the answer in a few minutes' time. Let me just quickly repeat a few things that Ragni Piena has just told us. Milnor really is one of the giants of modern mathematics, and I think there are 3 things that people have in mind when they say that. One is, of course, that he's proved many famous theorems, and there's something about Milnor's theorems that they all seem to be very, very beautiful ones. Even if you can't understand the proofs, the statements are very, very striking. And another thing is that these theorems have been in a number of different areas, which means that he has really touched a very large proportion of modern mathematics. And finally, as we've already heard, he's an extremely good expositor. His books are legendary for their clarity and importance, and they've stood the test of time. Books that he's written decades ago are still being read with great profit now. And he's been honored in many ways before. He won a Fields Medal in 1962, a Wolf Prize in 1989. One remarkable achievement is that he's the only person ever to have won all 3 AMS Steele Prizes. One was for seminal contribution to research, one was for exposition, and one was for lifetime achievement. That last one came just this year. And now, of course, he has the Abel Prize as well. So let me try to say a little bit about his mathematics, and to do that I need to provide some background. I need to say a little bit about a very fundamental object in mathematics called a manifold. So I have 2 pictures of manifolds there. One is a sphere, and one is a torus. A torus is a sort of donut shape. And I should stress that when I say sphere and torus, I'm not talking about the interiors of these shapes, but just the surfaces themselves. So these are, we would call these 2-dimensional manifolds, because you need 2 coordinates to describe where you are. And what makes them manifolds is that if you look at a tiny piece of one of these 2 shapes, it looks rather like just a flat piece of paper. So a flat piece of paper we think of as 2-dimensional space. A manifold, we say, is locally Euclidean. That means that locally, in any little piece, it feels just like the sort of geometry that Euclid would have described. And when we walk around on the Earth's surface, for example, in a sense we're experiencing the fact that the surface of the Earth is a manifold, because it feels flat when you walk around. You don't sense the curvature of the Earth, except if you're going on long aeroplane journeys or something like that, and then we're not talking about local anymore, we're talking about global. So on a small scale, it feels flat and Euclidean. On a large scale, it's not flat and Euclidean, and that's what makes manifolds very interesting. There are 3 points that it's important to bear in mind for the discussion that I'm about to give. One is, I've just showed you some 2-dimensional manifolds, but you can have manifolds in any number of dimensions. As soon as you get beyond 2, it's rather hard to picture. Even 3-dimensional manifolds, it's fine to imagine what being locally 3-dimensional is like, because it just means it's like what we experience in space. Not so easy to think what it might mean for the whole of space to curve round and meet itself or something like that. But in fact, the point about manifolds is precisely that it gives you the mathematical language to make sense of those sorts of ideas. So we can talk about three-dimensional spheres. So those, you could think of those as boundaries of four-dimensional balls. But a second important point about manifolds is that you don't have to. Manifolds have intrinsic descriptions. What that means is that you can talk about a manifold without talking about some bigger space in which that manifold lives. So when you see a picture of a two-dimensional sphere, it's living inside 3 dimensions. But you can actually, the whole theory of manifolds, you can get by just talking about 2 dimensions. But if you're not used to them, I recommend imagining that there is some larger dimensional space, and it won't be too much of a problem for this talk. And the third thing, which is a little more complicated, is that there are two, well, there are more than two, but there are two senses that I want to focus on this phrase that I mentioned earlier, locally Euclidean, what it means for a manifold to be like Euclidean space if you look at a small part of it. Let me give some idea of what these two notions of similarity are. So one is called topological equivalence. We say that two shapes are topologically equivalent if you can find some continuous correspondence between the first shape and the second shape. So an example here, a cube is topologically equivalent to a sphere. You can see that these diagrams show you how you could take a point in the cube and have an associated point in the sphere. And if you move your point around in the cube in a continuous way, then the corresponding point in the sphere will also move around in a continuous way. A famous example that people give of topological equivalence that I feel I have to give is that a teacup is topologically equivalent to a donut. By the way, the mathematical term for topologically equivalent is homeomorphic, and I may accidentally use that word later on. So to see that a teacup is topologically equivalent to a donut, you imagine that the surface, so I'm thinking about the surface of the teacup, the bottom of the bit inside the teacup sort of comes up until it reaches the top, and then the whole sort of cup part shrinks down, and you end up with a donut shape. And so we say that there's a joke that a topologist has the teacup and the donut in a restaurant, and they can't tell which is which. So now there's another sort of similarity. This is called not homeomorphism, but diffeomorphism. Now, I'm really not going to say exactly what this means. I think the thing to think about is that a diffeomorphism is like a homeomorphism, but the one-to-one correspondence you have between your two shapes has to be smooth. So for a homeomorphism, if you take a continuous path, but what does smooth mean, first of all? Smooth means you don't have kinks. All the bends have to be kind of, the direction must change in a gradual way rather than in a sudden way. So for a continuous one-to-one correspondence, if I've got my shape here and another shape here, as I move a point around in this shape in a continuous way, the corresponding point over here must move in a continuous way. But it doesn't matter if you could have this one not having a sharp bend, but over here there might be a sharp bend. So that would be, that would still count as continuous as long as you didn't jump anywhere. For a smooth correspondence, as long as the path over here doesn't change direction suddenly, then the path over here is not allowed to change direction. Somehow smooth is like a continuous correspondence, but there mustn't be any sharp corners. The graph has no sharp bends. I put that in inverted commas because if you think of most graphs, you have a one-dimensional axis and a one-dimensional axis, and then a smooth graph is one that sort of moves with no sudden changes of direction. But here we're talking about a multi-dimensional x-axis and a multi-dimensional y-axis, and so if, say, the x-axis has 3 dimensions and the y-axis has 3 dimensions, the graph will be a 6-dimensional object, not so easy to visualize. But nevertheless, if we have a sort of slogan like this, the graph has no sharp bends, I think we can get somewhere. So let me tell you two things that are fairly clear, I think, intuitively. One is if you take a topological manifold, such as a cube, you can always find you can continuously distort it and get a smooth manifold, one which doesn't have corners and bends in it. And another is that if you take two smooth manifolds that are topologically equivalent, then although all you've shown is that they're topologically equivalent, you could find a smooth one-to-one correspondence. You could just move your topological one-to-one correspondence about a bit, just iron off the corners in the graph, and get it to be smooth. So I saw a few nods there. I now have to reveal that the second of those statements is not true. So one of Milnor's very famous results is if you take you can take a 7-dimensional sphere, and you can take another shape over here that looks smooth. It's topologically equivalent to a sphere. That means that you can find a one-to-one correspondence between the points in the sphere and the points in this other 7-dimensional shape, and it's continuous. So in a certain sense, this shape is spherical. But even though this one is smooth, and the sphere is as smooth as can be, you can't actually find a smooth correspondence between the two. It's difficult to get your head around. You have two smooth things. They're the same shape from the topological point of view, and yet they're not the same shape from the smooth point of view. This came as a major surprise, and I hope that if I manage to get you to believe what I said in the previous slide, you can share that surprise to some small extent. In fact, even Milnor was surprised. This is what he had to say. When I first came upon such an example in the mid-50s, I was very puzzled and didn't know what to make of it. At first, I thought I'd found a counterexample to the generalized Poincare conjecture in dimension 7, but careful study showed that the manifold really was homeomorphic to S7. S7 is the name for the 7-dimensional sphere. Thus, there exists a differentiable structure on S7, not diffeomorphic to the standard one. And Milnor coined the term exotic sphere to describe these shapes, and I think this is a very justified term because they are extraordinary things. Even having thought about this for a few weeks, I find it very, very hard to understand why you can't just take your continuous correspondence and just iron out the creases and make it into a smooth correspondence, but I have to take it on trust that you can't do that. Somehow I think what happens, and I hope to ask John Milnor himself whether this is an accurate picture of what goes on. When you get into 7 dimensions, it can be the case that these creases that you have, when you try to iron them out, you can iron them out from one place, but you necessarily push them to somewhere else. And however much you try to iron them out, they always move around and stay there somewhere. And there are results in topology that have that sort of flavor. Very briefly, another very surprising fact about exotic spheres is that they're not as exotic as all that. What I mean by that is they have very exotic properties, but the way you make them, at least to a mathematician with a little bit of experience, seems extremely simple. What Milnor did was to take copies of S3 cross D4. And what that means, S3 is a 3-dimensional sphere, D4 is a 4-dimensional solid sphere, so with a 3-dimensional boundary. There's a way you can multiply two shapes together. Let's not worry too much about that. He took 2 copies of this product of an S3 with a D4 and glued them together along their boundaries. And the way he glued them used multiplication of quaternions. Quaternions are 4-dimensional numbers. Just as complex numbers are 2-dimensional numbers, quaternions are 4-dimensional numbers. Quaternions of size 1, length 1, form a 3-dimensional sphere and give us a very nice way of multiplying points in a 3-dimensional sphere together. And with the help of that notion of multiplication, he was able to glue copies of S3 cross D4 together and produce an exotic sphere. Another way of thinking about it that emerged later, which may be a little easier to grasp, you take 2 7-dimensional hemispheres. So you take a 7-dimensional sphere, cut it along the equator, and then you have 2 7-dimensional hemispheres. Then you re-glue them, but instead of gluing them so that each point in the equator glues exactly to the corresponding point in the other hemisphere, you use some other clever way of making the points correspond to each other. And if you can find a smooth correspondence between points on the northern equator and points on the southern equator that's not the obvious one, and you get an object known as a twisted sphere. And that again is an exotic sphere. Of course, the proofs, you have to prove that they are topologically spheres and they're not smooth spheres. And both those steps, particularly the second, are quite sophisticated. Well, once you've got one exotic sphere, you could ask just how many there are. And now we come back to the question from earlier on. This is a table of the number of differentiable structures in each dimension, starting in 1. So that question mark says that nobody actually knows what the answer is in 4 dimensions. It could be 1, It could be some finite number, or there could even, for all we know, be infinitely many exotic spheres in 4 dimensions. So actually I cheated and started at 5 dimensions in the little IQ puzzle that I started with. And so what is the answer? The next term in this sequence is 24. Anybody who managed to work that out deserves next year's Abel Prize, I think. But this was actually worked out by Milnor and Michel Gowers, as we heard, in fact. The first obvious fact is also false. So Michel Gowers showed that there's a 10-dimensional topological manifold. That's one it's allowed to have little bends in it and so on, that you can't smooth off. It has no differentiable structure at all. So I think the moral from that is manifolds are very, very strange, or much more interesting things than we thought. Just before I move on, actually, I want to say something. In mathematics, people often have counterexamples to long-established conjectures. Sometimes these are very destructive. The conjecture is made because people want a theory, and they get stuck at a certain point, so they make a conjecture, and then somebody shows that there's a counterexample to that conjecture, and that sort of kills the theory. These examples have had exactly the opposite effect. They have shown that there's an interesting theory of differentiable manifolds that is distinct from the theory of topological manifolds. So these examples have actually opened out an entire theory. The entire subject of differential topology was born with the discovery of exotic spheres. Now, another thing we like to do with manifolds is triangulate them. So I've shown, if you look at this picture, you'll get an idea of what I mean. You just take your manifold, here's a sphere, and you divide it up into little triangles. You may have to, of course, that's not an exact sphere because triangles are flat. We don't mind about that as long as it's topologically a sphere, that's fine. The reason that's good is that triangles are small pieces that are easy to understand, so then our focus of attention just comes on how the triangles are joined up together, and that turns it into what we would call a more combinatorial problem. Because a triangle you can specify with just a sort of finite amount of data and how they're joined together. Just to give an idea, you can triangulate things in higher dimensions. I'm not sure how easy it is to see what's going on in this picture. This is sort of a portion of space cut up into tetrahedra. And the notion of triangulation makes sense in all dimensions. And the Hauptvermutung that was mentioned earlier asks a question that initially may look a little bit, you may wonder what is interesting about it, but the question is, do any 2 triangulations have a common refinement? So what that means is if I take 2 triangulations of the same manifold, the thing is, if we're going to use triangulations to help us understand the manifold, we would like to be confident that if we take 2 different triangulations, we'll get the same answers out about the manifold. And one circumstance under which you can be confident that you get the same answers, it turns out, is if the first triangulation can be divided up into smaller triangles, and that gives you the second triangulation. We say then the second triangulation is a refinement of the first triangulation. So that means that if 2 triangulations have a common refinement, there's some smaller triangulation that refines both the 2 big triangulations, then we can be confident that the 2 big triangulations are telling us the same information about the manifold. So it was asked in 1908 whether 2 triangulations always have a common refinement. Another question you could ask, can every topological manifold be triangulated at all? It seems pretty obvious that it can. Indeed, it seems, if you think about 2-dimensional manifolds, you get the impression that the answers to both these 2 questions are yes. I imagine you're not quite so confident now because of, and indeed, the Hauptvermutung, which means main conjecture in German, is false. And Milnor found a counterexample in 1961, actually for a more general form of the conjecture for objects called triangulable spaces. These are, for the mathematician, these are spaces that are homeomorphic to simplicial complexes. But it's actually false for manifolds as well. That was discovered by Andrew Casson and Dennis Sullivan. And Michael Friedman in 1982 found that there's a 4-dimensional manifold that has no triangulation whatsoever. And again, I'm afraid I have very little intuition about how such a thing could exist. When I think about a 4-dimensional manifold, I just think, stick some points around, join them up with some lines, and join the lines up with some faces, and bingo, there's your triangulation. But unfortunately, for some reason, that can't be done. I think probably you can do it in a small portion of space, but as you sort of go around the 4 manifold, it meets up somewhere and you find that you can't complete the triangulation. Another result of Milnor, unfortunately I'm not going to have time to, this is the last one I'm going to be able to discuss in any detail because of lack of time. This was a very early result of his. How curved must a knot be? A knot is something like you see in this picture. It's a piece of string that joins up to itself, and you can't untie it into a circle. Now, if you want to make a piece of string into a circle, obviously you have to curve it to some extent. And it seems fairly clear that if you want to make it into a knot, you have to curve it a bit more. If you look at this picture, it sort of goes round twice, and it's really quite curved at those 3 points. So we could ask, how curved must a knot be? Now, of course, we have to make sense of the question. So for that, we need a notion of what's called curvature. If you've got a curve, and you look at a point P on the curve, what you do, roughly speaking, is you take the circle that best approximates the curve at the point P, as I've drawn here, and you look at its radius, and the reciprocal of the radius is the curvature at that point. So the smaller the circle, the bigger the radius, the smaller the radius, the bigger the reciprocal of the radius, and therefore the bigger the curvature. That makes sense. The more sort of quickly it goes round, the smaller the circle will be, but the more curved it is. And a concept of total curvature of a curve, what that means is you take the average curvature at each point, multiply that by the length of the curve, and that gets you the total curvature. So for a circle of radius r, the radius of curvature at each point is r. So 1 over the radius is 1 over r, and the length is 2 pi r. Multiply those together and you get 2 pi. So for any circle, whatever its radius, the total curvature is 2 pi. You can either make it small, in which case you get a small length, but you get quite big curvature, or you can make it big, in which case you get a big length and a smaller curvature, and however you do it, you end up with 2 pi. In fact, the same is sort of true for any curve in the plane, but I won't go into that, I think. So Milnor showed that a knotted curve has to have total curvature twice as much as that for a circle. In fact, slightly more than twice as much. So very roughly what that's telling us is that, as you saw for the picture of the knot, if you're going to knot your curve, it has to go around at least twice, and if it goes around exactly twice, it'll have to stay in the plane and cross itself, so it has to go around a little bit more than twice in order not to stick in one plane and cross itself. And this was proved independently by Milnor and István Fari. Milnor was only 19 when he proved this result. This is a slightly irrelevant slide, but it has I have three reasons. Each one on its own would be insufficient, but I think the three together add up to enough of a reason. So the first reason is that this is the hammer of Thor, and so I would associate that with a little bit with Norse mythology and therefore where we are now. The second thing is that the hammer of Thor is called Milnir. I don't know if that's a good pronunciation, but it was tantalizingly close to an anagram of Milner. And the third thing is that if you look closely at this particular rendition of Milnir, you see there are two trefoil knots on it. So it was just too good not to put there. Let me very briefly talk about some other work of John Milnor. But we've actually just heard about that briefly, so I will be quite quick. There's a concept called growth in groups that has turned out to be of huge importance. It's a focus of very intensive research even today. Milnor and Wolff proved a theorem that says, I'll just tell you the words here, that every solvable finitely generated group of polynomial growth is virtually nilpotent. The main reason I'm saying that without explaining what it means is just to say that if you omit the condition of solvable, you get a more general theorem that was proved by Gromov, and it's one of Gromov's most famous theorems, and he was the Abel Prize winner 2 years ago. So this is just some indication of the kind of influence that Milnor has had on other mathematicians. A similar story with algebraic K-theory. K-theory is well, there are all sorts of things one can say about it, but we could think of it as a topological theory about homology classes. You can think of a homology class as something like a submanifold of a manifold. I'm oversimplifying very, very drastically. But algebraic geometers like to realize these submanifolds in an algebraic way. They like them to be solution sets of polynomials. But if you want to do that, it raises all sorts of extraordinary difficulties. And the subject of algebraic K-theory was a theory that people realized must be out there and that would be useful for tackling some of these difficulties. But it was very hard to come up with the appropriate definitions for that theory. And one of the things that Milnor did was to work out the correct definition of an object called the K2 group of a ring A. He made a conjecture connected with this, as we heard earlier, that was solved by Vladimir Vervodsky. It was a sufficiently important conjecture that earned Vervodsky a Fields Medal. So another example where Milnor's work has been very important in the work of other very important work. And we also heard that he did significant work in dynamics. One part of his work is in holomorphic dynamics. And again, I won't say anything about this except to say that you may have seen descriptions of chaos theory and amazing pictures that look things like that. That's the sort of area, or it's one part of the area in which Milnor has been working recently.